There'd be a little bit of math involved, but it's not going to be anything crazy. Talk about the Earth a bit. Ground school will cover things that, basic things that we need to know in order to plan a flight. Some of the challenges that I came across with trying to import all this aeronautical data into Postgres. And then we'll talk a little bit about how I display the information to the end users. I have some time left over at the end for Q&A, but if you have any questions throughout the presentation, just go ahead and ask away. All right, my day job is a sysadmin at CBC. We have 2 Postgres servers there, but it doesn't really keep me interested. So after hours, I'm a PHP programmer, and me and my partner set up a website called World Flight Planner. In flight school, they teach you to plan flights using pen and paper, and charts, and rulers. And for a simple flight, it takes you probably 15-20 minutes to gather all the information that you need. And 3 hours is too long, too painful. So I decided to come up with a tool whereby fellow pilots can go ahead and plan the flight online, and all the information will be aggregated and downloaded automatically. We launched in 2009, and the scope right now is just Canada, and we're slowly increasing support for additional countries as we get the data from those countries. The front end was written by my partner in Rails, and the back end is what I'm responsible for, written in PHP and Postgres.
It's on Perl too.
Yeah, a Perl for intermediary processing between the data that we get from different sources and updating it to Postgres. Here's an example screenshot of some of the data that's available. The magenta line and the yellow line is various airspaces around Ottawa. This band here is weather radar. Paul in his keynote mentioned that with Postgres you have each table is a different layer. So one table is the airspace, another table, well, sort of, is the weather data. And we layer those tables on top of each other on the map. Here's a sample flight from Toronto down here to Ottawa, and we have this waypoint in the middle here. So we're allowed to display various pieces of information such as airports. These are seaplane bases, so the airplanes with boats can land. Heliports for the helicopters. Airspace, the red stuff is restricted airspace, so you can't fly in those areas. And then there's different types of airspace, as you can see here, green and magenta, for various other all these different things. Pilots are worried about 2 things: running out of gas and running into things. So we have to carefully plan the distances that it takes to get to point A to point B, how long it's going to take us to get there, how much fuel we're going to burn, and if we're going to run into anything. So this is a typical flight plan. We have a starting point, any intermediary points, and a destination. The altitude we're going to be flying at, how much distance we have left, the wind, our airspeed, our ground speed, our estimated time en route, and how much fuel we used, and how much fuel we have remaining. And then this little tidbit down here, MOPA, which stands for minimum obstacle clearance altitude. This is the number that we have to make sure we're above, and we're flying so we don't run into anything. So all the elevation data is stored, or will be stored in Postgres. So we can do a simple select saying, hey, is my route going to, at 500 feet, am I going to fly into any terrain? I'm going to fly into that type of thing. So data that we have so far is about 1 gig. We have over 150,000 points, 2,900 unique polygons, 800 unique line strings, and over 1.6 million points of weather data, which covers 15 different altitudes over the course of the next 3 days.
You said you're keeping an altitude data.
Yes.
So this you need to have like a digital elevation model.
Yes, and I'll talk about
1 gigabyte.
Yes, so this is the information that's only stored in the PostgreSQL.
House.
Now, I'm going to talk about that in a second. So, some of the tools that we use, obviously Postgres and PostGIS. UDIG is a desktop GIS sort of application that allows you to visualize the points and polygons and lines and whatnot on your desktop. OpenLayers is sort of like the Google Map API, but it's open and you can do more cooler things with it. MapNig and MapServer, I'll talk a little bit more about those two later. So why did we pick Postgres and PostGIS? Well, I think it's really cool to be able to answer questions using SQL. So if I want to know how long a route is, I just do select, distance or length, between these 2 points, and boom, I get the answer. And I get the answer fast. I sort of did some tests with MySQL. The spatial support isn't very good, and it wasn't very fast. But this information also has to be accurate. So it allows us to only filter. PostGIS allows me to filter out stuff I don't need, so I don't overwhelm the pile with information it doesn't require. And here's an example of using in-car building like GPS in car. That's not very accurate. We can't really do that when it comes to flying because we need to know how much fuel we're going to use, and we can't just pull over the side of the road if we're out of gas. So PostGIS and Postgres allow us to be pretty accurate. So there's 2 main types of geographic data, 2 main formats. One is the vector format. And we use specifically 3 different types. We use a point to represent things like airports, navigational aids, a line string, which is multiple points in a specific order. We use those for the actual route that you're flying, or what are called airways. Airways are like highways in the sky that specific aircraft will follow. And we also use polygons, which is just a closed line string. And we use that to define things like airspace. So here's all 3 types on the same map. We have points, like airports, polygons, airspace, and then these purple lines are airways. So it allows air traffic control to route the majority of the traffic through a known path. It's a little bit easier to manage aircraft that way, as opposed to having everybody flying all different directions. The other type is raster type, and this we were talking about with the elevation data. Rasters are 3-dimensional data. So you have a specific point, and at that point you can have multiple pieces of information. In regards to weather information, a specific point on the Earth will have weather information for different altitudes. So unfortunately, PostGIS doesn't support storing rasters in the database yet. So for in this situation, we just store the files on disk.
Probably do by the way.
Yeah, and again, I'll talk about that later on. So the actual digital elevation data that we use, only for Canada, is about 100 gigabytes. So it's
You get it from geodatabase.
no, I get it from STRM, SRTM.
Moreover.
Yeah. I think it's 30-second resolution. Alright. So, the shortest distance between 2 points is a straight line. And
Great circle.
on a plane, yes, exactly. And the math to figure this out is relatively simple. Yeah, it's relatively simple.
Actually, it's a great circle, but we won't go into that.
Well, we are.
Okay.
So, unfortunately, we don't live on a flat Earth.
So, I think we do.
So, the math is a little more complex when it comes to dealing with paths on a sphere. But thankfully, PostGIS can take care of all this for me. I don't know anything about math. I never went to university or college. So, I know I sort of understand what this means, but if I can just use a function instead, then why not? Just throwing a little monkey wrench. The Earth isn't perfectly round; it's actually an ellipsoid. So it's important to know the difference between the two because it actually affects your calculations. So if we were to take a flight from Ottawa to Amsterdam, if the Earth was a perfect sphere, it would be 5,631 kilometers long. But because the Earth is not a sphere, but it's actually a oblong, that distance is actually a little bit longer. ICAO is the International Civil Aviation Organization, and they define the standards that we use for storing geographic information when it comes to flying. And they specify the WGS 84 geoid as the digital representation of the Earth. So
that's the distance at sea level, and then flying at altitude, is it basically longer?
No, yeah, that's the distance at sea level. When we're planning for flying, we don't really account for the distance traveled vertically.
No, I meant because it's a larger sphere, if you add another few kilometers of radius. You're flying a distance at an altitude, so
Your arc length is gonna be more.
Yeah.
Longer.
I don't think it's significant because
No, you don't include that.
we don't include it in there, so it's really.
That's why they have the 20-minute rule.
Yeah. Yeah, we account for little anomalies in the calculation, so I don't think it's significant.
What about projection?
Next slide.
I was going to ask that.
Let the poor man give his talk.
So,
Maybe it's hard to do that.
so we're forced into using ICAO standard for defining certain things. So the problem is that we need to be able to project the Earth onto a flat surface when we want to see it on the map. So we use these things called projections, and there's a whole bunch of different types. The most popular one that I'm sure you're familiar with is the repeater projection. And if we were to plot that line on a curved line that's on a flat surface, it would actually show up as an arc. But there is another projection called the dynamic projection. Dynamic. And what this projection does is it takes your great circle and projects it as a flat line. But unfortunately, Google Earth doesn't support, or Google Maps doesn't support this type of projection.
I got a story about that if you want to hear it.
Yeah, but
So,
you still have a problem because the projections they are very area specific.
yes.
And Mercator is a universal one, but
Yeah.
it won't work for all the.
Yeah, so for example, like I can't see this portion of the world here, like south of Russia, but on Mercator I could see the entire world. Here's another example of the same problem. If we were to draw a straight line on the Mercator projection, which is the blue one here, it actually appears as a curved line on the Dynamic projection, and vice versa. But again, this projection is kind of useless. Well, it's not useless, but I can't find any sort of mapping software that supports this projection. Or there's no base maps that support this projection.
We'll get into that later.
But I can use them like Open Layers or Google Video like that. So here's how I do it in our software. Nice big fat arc on the Mercator projection. So pilots want to get from A to B as quickly as possible. You don't have things like roads sticking in our way. And we can use tailwinds. At altitude, tailwinds can be as high as 200 kilometers an hour, so you can save on fuel and get there faster. But we also have other problems too, in that going the opposite direction, we'll have a headwind instead, which slows us down. And there's some sort of airspace that we can't go through. I know a lot of pilots are frustrated when the U.S. president is flying close a huge big swath of airspace around his airplane as he's moving across the country. So in the cockpit, we use a couple of different tools. GPS is being mainly the top one. Private pilots like myself use compass and charts because we don't have fancy GPS in our airplanes.
The navigation.
Yeah, the guys up north where their compass is useless, they'll use the stars.
My dad's actually the last certified one left.
Air traffic control helps us by giving us vectors to different directions where we want to go, and the radio navigation aids are, again, an old school way of getting everything to go. So we need to be able to do this again accurately. You know, in order to do this, we need to have specific information, mainly being the locations of the airport, so where we're leaving and where we're going to. Any navigational aids along the way, airspace definitions, and wind data, so we know if we're going to have a headwind or a tailwind for fuel calculations. So the first challenge I ran into was with the navigational aids, and I lump airports in there as well because they can be used as a navigational aid. ICAO was kind enough to give us a unique identifier for each airport in the world, but the navigational aids within each country is up to the country themselves to name. So, in Ottawa we have a non-directional beacon called OW, and there's also one called OW in the US, in Owensboro and Norwood. So, the problem I had was what's my primary key? What's my unique what can I use as a unique identifier for my records in my database? And this is what ICAO, they don't use the same ISO standards for country abbreviations, so they don't use CA for Canada or USA for the United States. This is their scheme that they come up with. And in some situations, like in Russia and China, Brazil, they further segmented up the country into different regions using different codes. But the United States being the opposite side, was just stick with K. So what I had to do was actually break up the US into 6 different parts. I ran a query to find where the navies were with the same name, where they were geographically placed, and it worked out perfectly that I cut them up by state, and I decided on making the United States actually 7 separate countries in my database. Yep, so my primary key is the country, the navig type, and the identifier. And this is what my navig table looks like. I have an internal ID that I always create with my tables. The name of the navig, what country it's in. This references my country table. I have some various other information like city and state that I use for my own personal use. Here's the PostgreSQL geometry column. And we keep track of the elevation of the airports as well. Any questions so far? So, if here's a query that says, give me all the navigations identifiers OW. So I do a couple joins between my country table and my navig type table, and I can see that there's one in Russia, Indonesia, there's one in Canada, there's in Ottawa. But the US actually has 3 in the same country, but because it's split up into 7 different countries, or 7 different logical countries, I'm able to use it. I'm just showing you this slide to illustrate how PostGIS stores its information. It's actually a binary and then when you use select, it just turns it to the hex value. But you can use the as text function to determine the geometry type and coordinates for it.
The elevation is feet or meters?
It's in feet. So again, ICAO states that elevations have to be in feet above mean sea level. So Amsterdam is actually below sea level. The big challenge I had was dealing with airspace. Airspace is quite complex. Some of it's simple, like a simple circle, and then some of it is what I call like Pac-Man shaped or pie shaped. So you have a triangle with a rounded edge. And to complicate things even more, this is how I get the data from various governmental or organizations in plain human readable legal format. So, we have two airports, Buttonville and Markham, which is here and here. So if I was to draw this out on Blackboard, I would have point 1 being this point here. Okay, we go up to this point, and then we do what? A clockwise arc like that, then a counterclockwise arc like this, another point, another point, another point. So I wrote a Perl script to parse this out, and I use various Postgres functions to create the arcs for me. So this is the specific piece right here, up, and then we have another little arc down here. So this is this airport's airspace within this green boundary. In Postgres, there's two ways to store arcs. One is to store them as a lot of individual lines. So what you can do is you actually draw points on the arc, and then they're really straight line strings all the way around. Or you can use what's called the circular line string geometry type. And all that does is that just stores your starting point, your ending point, and some other point along the arc. And then that's it. And then it's up to the renderer to actually render the arc. What I ended up doing was create a new function called createArc. Because what we had was the starting point, the ending point, and the center of the circle along that arc. Which, with the circular line string, I need to find the third point on the arc, not the center. So, this nasty function, which was, by the way, the first ever Postgres function I ever wrote, does this for me.
You really kind of dove in on the deep end there.
Yeah. Yes. And to complicate things even more, when I wanted to add Australian airspace, they don't use clockwise or counterclockwise. They use major or minor arcs. So now I have to figure out which is the longer arc. Which way do I go?
Oh.
Counterclockwise one longer or clockwise one longer? So I have a couple of crazy if statements and like stuff in here to take care of that. So this is what I get. This is what my function spits out. Here is the first. The black text is from here all the way to here. The green is this inner portion here, and then the blue is the rest. So, I mean, theoretically you could, because these are straight lines, theoretically you could sort of skirt because it's more of not an octagon, but it's a multi-sided polygon. But for the purposes of displaying this on a map, it works pretty well. It's like a real circle. If we do it all over again, I would actually use the proper circular curve geometry type. It would make this a lot simpler. Instead of having all this crap here, we would just have 3 points. Yeah, I do. I actually have a bug open with UDig because it doesn't support those types of displaying those types of geometries. It's been open since 2008, so it's hard to visualize or debug my code when I can't see it on the screen. So that's one of the reasons why I decided to do it this other way.
Did you try with QGIS?
Yes, and I think the same thing. What I could do is I could use the curve to line function, which converts it to a line, but I'm a perfectionist. I want to actually have it drawn properly. So the other problem we had was with storing raster data. Postgres doesn't allow us to store the raster data in the database properly, and we get this data from the the weather from NOAA or from Environment Canada for the winds and the weather and whatnot. And they use a format called GRID, which stands for gridded binary. So, solution one is we don't store the raster data in the database, and we have it actually on disk. And I use map server to query points along my route and to give me the elevation data from the raster files on disk. So this is one of the things you can see in the software, whereby I am planning to fly 1,500 feet along my route. Am I going to hit anything along the way? Looks like I'm not. It also allows us to visualize this on the map itself. The yellow shaded area is terrain within 1,000 feet of my planned altitude, and the red is within 100 feet of my planned altitude. So this is really handy in the mountainous areas. It's slow because I actually have to fetch the data off the disk through map server, and it's not actually stored in Postgres. And then we can use the array type. And this is the first time I've ever used an array inside the database.
Whoa.
It's slow, but the good thing is that none of my queries are going to try, there's no where clauses on the actual array itself. So I'm only going to fetch my data on the actual location of where I want the information. So what we do is I take the gridded binary information from the NOAA, convert it to a CSV or the utility they give us, then you scroll and massage the data, and then just copy and import that data into Postgres. And then what we do is we have each element in the array as weather information for a specific altitude. So at this particular location, at this particular time, and at this particular altitude, the temperature is minus 42 degrees Celsius, and we have wind vectors for the vertical and horizontal components of the wind. It's really fast because I index on the point and on the time. So I'm like, any weather for this point at this time, and boom, I have the array. And then my software can just go and figure out which array position is which altitude that I want, and then displays that on the screen.
So we build it for every point?
Yeah. So this table is the 1.6 million record table. I think it's 1 degree latitude resolution.
1 degree.
Yeah, it's 1 degree.
And then what in between is that contemporary or?
No, it don't show anything at all.
It's 1 degree, it's 100 kilometers.
Yeah,
right?
yeah. So the great thing is, well, in my world, in the pilot world, is this is way better resolution than we've ever gotten before. Because the old school way was you have various cities in your country throw up a weather balloon, and it could be like 500 kilometers apart, or 600 kilometers apart.
Have you tried tiling?
Certainly.
So you can take the heat or raster for tile. You can tile with the boundary of mesh, like 1 latitude.
Yeah.
Then you can take that tile, throw it in the database, add that whatever integer array, double array, and then because you know the coordinates, you can take the whole tile right away from database and that.
Yeah.
And then you can just take code procedure for the time.
Yeah. Yeah. No, this is definitely another way of doing it. Yeah. This is fast for what we use it for, so I think it's simple.
Yeah, I was wondering, this is all forecasted data, but do you use any observations to give like an up-to-date forecast to pilots?
Yeah, but the observation data to me is not in grid format. Just a Netar format, so it's just a text format. So what we can do is we can use map server to display that weather information on the map. So these are wind bars, which just the angles tells us which direction the wind is coming from, and the flags tell us which how strong the wind is. Okay. So now we actually want to plan the flight. It's really easy for us to find out how long our track is going to be because we can use the ST distance function. Fortunately, this function returns the Euclidean distance, which is the distance on the flat plane. But thankfully, Postgres gives us the distance on the spheroid instead. So no complicated math or great circle crap to worry about. You just plug in the starting point, which is Amsterdam, or which is Ottawa, your ending point, or actually that was reversed. and the spheroid that you want to calculate the distance on, and then boom, you get 5,648. Well, that's in meters, by the way. This is kind of funny. Qantas in 2007 had on their little air safety card, you weren't allowed to use Furbies on the airplane. But pilots really want to know where the closest airports are along the route in case they have to make an emergency landing. If they run out of fuel, or someone turns on the Furbies, causes the airplane to go haywire. There's a few ways we can do this. We can use the distance function. So what we can do is we can take our line string and then go through every record in my naive table and say what's the distance to this place, what's the distance to this place, in order to sort by that. Or we can use what's called the within function. So the way that one works is, say we have our route in here. I'll buffer, say I want to get all the airports within a 20-kilometer radius. I use the buffer command, which actually, or function, actually creates this line, changes this line string into a polygon, and then I can say, give me all the airports that are within that particular space. Or there is a pretty generic function called the nearest neighbor function on Boston's GIS website, written by Regina, that we can use to find the closest neighbors to my line string. But for my purpose, the distance one works well. It's fast enough for us. So I can say, give me all the airports, which is Navi type 1, that is within a 20-kilometer distance from this line string, which is my route. And these are the airports that I get along that line. I'm sure you haven't heard of some of these airports.
Like YTZ?
Why is YTZ or not? Because I'm departing from Buttonville and not Toronto, a little further north. So it's probably within that 20K. So we're like, well, I never heard of Carlton Place. So some of the airports that I'm getting back are too small. My airplane can't land on there because it's probably a grass strip or the runway's too small. So I have the runway length.
Airplane do you have?
Yeah, well, depends how rich you are, right?
Exactly. How much money are you making off this?
Yeah, right. So what I can do is I can do.
CBC's government.
Yeah, it must be, yeah. It's flying a Learjet 40, I think.
Okay, so my Learjet can only land on airports that have a runway length of 4,000 feet or longer.
Exactly, yeah.
So I can now do a join with another table, and I actually get airports that are suitable for emergency landing.
So when you took off and the one you took
Yeah, you know what? Sometimes the quickest way is just to turn around and go back, right? So, getting your pilot's license, they drill it into all the emergency procedures you have to do. And one of the hardest things I found was I'm flying the airplane, it's about to crash, or I need to land right away. Now I've got to dig through my chart and try to find where the nearest airport is that's suitable for landing. This way, I have the list already prepared, and I know where to look on my chart for airport, for example. So that's definitely airspace. We need to know what airspace we're going to fly through, so we know who to talk to, air traffic controller to talk to, or we're going to get shot down by flying through restricted airspace. So the airspace that we have is the polygons, and we can do a simple SQL query again using the intersects function to find out if my route intersects with any of the airspace in the database. And the flight from Toronto to Ottawa, I see them flying through various different types of airspace. Thankfully, none of them is Class F, which is restricted airspace. So we're good to go. I don't know if you can see this properly. So, like, do you have any ideas of what this is showing? Yeah. Time zones. time zones from the time zone file. It's easy info over what's called.
Kind of right, number one.
And he converted them to shape files. It's actually pretty cool. And so what I've done is I've taken the shape file and imported it into PostgreSQL to be able to get the local time that you're going to be arriving at your destination. So the way I do that is I take your destination airport. Is it within any of the geometries from that time zone shape file? This tells me that it has to be within 0.01 ID. And then get the time zone ID that I can then use to offset my times. Pilot reports are really cool. So if the pilot's up in the air and he's flying around and he sees something that wasn't forecast, he can radio into air traffic control and say, hey, you know what, you forecast to be like sunny, but it's raining where I am. So
Use rock their pilot.
yeah, exactly. Please let me know, because other pilots know that this, so they don't get screwed like I just got.
That's what happened at the volcano, actually. We first reported by a pilot.
Yeah. So
Saved so many people's lives.
yeah, well that's it. It's really important. Now, unfortunately, the air traffic system is really integrated, and this is what I get if I was a planner from the systems. So I'll just quickly go over what it means. There's a timestamp for when the report was filed. This tells me where it is. It's 125-degree bearing, 50 nautical miles from this particular airport at 12:31. This is the type of aircraft he was in. And then this is the important information. So he's saying the ceilings are really low, 50 miles southeast of this airport, and he's en route to this particular airport. So, old school way, I look it up. Okay, where's CYXZ? Find it. Okay, and I take my ruler and draw 50 miles southeast of that.
While you're flying the airplane.
Yeah, well, or even before I do, right? So the plan, all this little stuff adds up when you're planning your flight. So, what I do is I use Perl to parse all this crap out, right? Figure out where it is, time. Sorry?
Pearl to the rescue again.
Please let the guy finish his talk.
Sorry.
And then I use two specific functions to plot this on the map. So, this little icon here is the location he's talking about. Here's the airport he departed from, and this is the airport down here that he's going to. So the way I do it is I know that the starting point is located here. So it's 50 miles away, so I use st-translate to say, hey, move my point 50 miles away. And then I use another function that somebody else wrote that's available on the PostgreSQL wiki that says rotate that point. So that I rotate this point around the original point by the bearing, which is 125 degrees. And that's how I get the location plot on the map. And when you do see on the map, you can click on the little eye and you can get the raw data. So you can control it and make sure you get the actual message. Severe weather is a big problem. And once again, we get crap like this. Let's see, within the 30 nautical mile line of here to here, thunderstorms popping out of 30,000 feet observed on radar, line moving eastward at 20 knots, little change in intensity. So if I was to read this, again, I'll take out my map, figure out where this point is on my map, figure out where this point is, and then just create a 30 nautical mile buffer around that line. So, in PostgreSQL, we create the line stream, so I use Perl to grab the points in my line, here and here, and then I use the scBuffer function to make sure it's 30 miles around that particular line. And these are the shapes that I get. So, these segments are various thunderstorms and whatnot, and it's really easy for me to figure out, hey, is my flight going to go through this area or not? And because I can use the st-intersects function, I can actually get my flight plan and say, hey, watch out, buddy, because within 40 miles of your trip, you're going to run into this particular piece of weather right here. So I used two main pieces of software to render the data, MapNIC and MapServer. MapNIC takes care of all of the layers. So all the airspace, and all the airspace, all of the airways, airports, navigational aids, and then just little blobs. Blob down here, airports, airways, those are all done by MapNIC. And it's pretty cool because it generates PNG tiles, right, and then overlays Google API or OpenLayers overlays. MapServer I use for overlaying the raster data. So the elevation data on top of that. It's a lot faster than using MapNIC to re-render the data. The raster data is already in a file form, it's already in an image format, so it's easy just to overlay that on top of the data. I use Google Earth sometimes to sort of pre-validate that the data in the database is correct before I analyze. And of course, upload the data. So the future. Paul mentioned in his keynote that Post just assumes that everything's on a flat plane. Starting in 1.5, we introduced what's called the geography type, which assumes that you're actually going to be on a sphere instead. So this is great because I don't have to use all the spheroidal functions. That's not a word. But it's kind of a little immature still. It doesn't have all the functions that I need. So I'm sort of stuck in limbo. One foot, some of my data is in the geography type, and some of my data is in the geometry type, and it has to be back and forth between them. But as more and more function support for geography comes about, I'm going to be converting my data over